Merci Simon pour cette primeur, and congrats again, Sébastien, on your PhD. We're glad to keep you around. There's a lot of stuff that you presented, so for whoever that couldn't speak and walk up to the mic for their questions, please do stick around, as Sébastien will with us. I'm going to present our next speaker, who is Dan Assouline, currently a postdoctoral researcher under the supervision of Yashua Benjo. His expertise lies in physics-informed deep learning for forecasting and modeling and its application to renewable energy, prediction and partial differential equation solving. So today he'll present his research on chronological series. So Dan, whenever you're ready, the floor is yours.
Hi guys. I'm just plugging 1 second in case. Okay, you see well? Okay, thank you for being here. So yes, I'll talk about energy prediction and especially time series forecasting for solar energy, but I put it in parentheses because theoretically it should be applicable to any kind of energy variable or weather related variable, hopefully. So, okay. So yes, what would we like to forecast renewable energy? Well, because it's another way to mitigate climate change. Why? Because it helps in the management of energy power plants. So to know how much energy I'm going to use, do I need to buy maybe another source of energy and put it in the grid? It's just very useful for this. So what would we like? It's to basically forecast solar irradiance within a useful horizon, so a few hours or maybe a day, maybe 2 days, but 1 day is usually good enough, at any point or solar station in the world where we want to have something like this, so basically power plants. The problem is, it is actually very hard to do forecasting for time series if you only base yourself on historical data in the past. If the weather was good yesterday, there's basically no reason why it would be good tomorrow, unless you have some kind of context. Why is it so good? Why is it so hard? Sorry. Because you can theoretically separate your time series into low frequencies and high frequencies. Low frequencies are basically looking like this, which is basically the main average, let's say the moving average, the main trend of your series. In case of solar radiation, it's very, very easy. It's like very nice curves like this. It's just due to the day and night seasonality. The high frequencies are responsible to what the solar radiation looks like in reality, which is this, which is significantly more difficult. And this is due to basically random processes like the presence of clouds. And because of this, pure time series models have problems to try to evaluate the high frequencies. So basically this little wiggles over there, it's quite hard. So a potential solution to this problem is to try to use the context. So basically what happens around the station to try to gather more information. But how would we do this? So there are multiple ways, and basically these multiple ways correspond to projects we're working on here at Mila. So what is the first idea? The most natural thing would be to try to predict the context, and then from the context, predict the solar radiation. What do I mean by context? One variable that is very enticing, that would be very useful, is the albedo. So what is the albedo? Is the reflection of the solar radiation on a surface and also on the atmosphere. So it's basically one of the most difficult things to predict. If you predict this, then basically you have mostly the solar radiation. Clouds are really responsible for this, so they're directly proportional to albedo. For example, this picture might seem like it's a picture of clouds, but actually it's just a picture of albedo with a nice color map that sets white to 1 and 0 to blue. So you can see how it's correlated. The good thing is, it's then correlated to what we call incoming shortwave radiation, which is basically the main component of solar radiation, in a very, very simple relationship that is like this, like 1 minus the albedo times the clear sky gives you the main component of the solar irradiance. What is the clear sky? It's what happens if you didn't have any clouds around. So it's like a cloud-free solar irradiance that we can compute anytime, anywhere. So it's like a really good proxy of what's happening in reality. an idea would be to just predict this, and then from this, you could actually predict the solar radiation at any pixel in the area of interest, but you have to base yourself on your current resolution. So if you have multiple stations in one pixel, then it becomes more difficult, but I'll talk about this after. Theoretically, what you could do for this is just to train a machine learning model based on historical data, like satellite data. And another feature that would be interesting is optical flow. So what is optical flow? It's basically the velocity of a pixel between two frames. It's just like in vision. You can compute the velocity of a pixel between two frames. If you have certain assumption, it's actually not so trivial mathematically, but it's quite easy to do. There are some libraries for it. And then when you're done with it, this is what it looks like. So on the left side is a water vapor channel, and on the right side is a visible channel at another wavelength. So you see on top of it, there's basically the little arrows, or okay, the resolution is not so great here, but velocity vectors at any point. So it gives you the information of where it's going to. And people strangely don't really use this all the time, but I think it's a very good information to play with. You could use it to do a naive forecast, or you could try to learn the velocity. But the easiest thing is just to add this as another feature in your model. So what we try first is to train some state-of-the-art video models to try to predict albedo. So very quickly, we use past albedo, space and time features. We have a resolution of 30 minutes, and we try to predict 4 hours in the future based on 4 hours in the past. So this is what we would like to predict, which is the albedo. Again, it looks like the clouds, but it's the albedo. And as well as possible. So this is, for example, an example of the models we trained. Each line is a different model, and the first line is a ground truth. So yeah, before developing new models, we wanted to see how good it could be. So it's not bad. The problem is, you see here in terms of mean absolute error or root mean square error, it's around, the best models do around 10% error, which is good. But when you increase the horizon, it significantly decreases the performance, and it gets pretty hard. And also, because we're focusing on trying to help solar stations at a particular pixel, it might not be at a high resolution. And then when you increase the resolution, the memory needs to increase, and you run into all kinds of problems. So we're thinking of another idea. What if we try to embed the context directly within the forecasting model to mix it with the historical data we have? And this way you could try to learn directly the spatio-temporal dependency. And that's what we did in a work that we just submitted to NeurIPS to try to use transformers. So using attention, for those who know a little bit about this, it's kind of everywhere these days, to predict the next day the global horizontal irradiance, so the main component of solar radiation. So the models look like this. You have your past contexts that are basically videos of radar channels at different wavelengths, the past time series at a point in space, and you can train it with multiple stations. And at the end, you have your prediction of the future. What we do is pretty, it's pretty natural. We try to encode the information of the spatial context. First, you tokenize, so you separate into different patches, GPT style. Really, like this is done all over for attention models. You feed it into a transformer. It's kind of paying attention to itself to try to compress the information in a like compressed vector. You do the same for the past time series, and then you merge the two in cross attention transformers, which basically, each side try to pay attention to the other side to see, okay, if a cloud comes around here, then it means that the day is not going to be a good day. You just fit it into another transformer, and at the end, we have a version where we have multiple quintile head, where each head basically learns a quantile instead of the mean, so you can output a distribution in order to have a prediction interval attached to your prediction, or you can just have one head that predicts just the mean. One important thing is, if you know about transformers, you know that this thing here, the positional encoding, is very important because in attention models, usually, not usually, you don't have the information of location, basically, of the patch you're trying to pay attention to. So you need some positional encoding. In this case, we use a rotary positional encoding, which gives you instead of the absolute position, it's the relative position of the current patch with respect to your station. So that's what makes it generalizable to any station, basically. Okay, very quickly, the data. So we have different components of solar radiance, clear sky, pressure, for 6 different locations. So it's like different stations in the world, and multiple channels of radar images at multiple wavelengths. So this is what it looked like. Some of them are visible, like this one here. So you see during the night, there's nothing. Some of them are invisible, so it's continuous data, all like it just never stops. And optical flow for the non-visible channels. So we keep the resolution at 30 minutes, and we have, if you look closely here, you see basically Europe and North Africa behind there. So that's our zone. And what we do is, we train on data that is, we do a split between time and space. So we train on some years, and then we test it on unobserved years, of course, and we do the same for stations. So yeah, the main idea is we want to try to be generalizable to a new station where the model was not trained. So here we have 6 stations that are kind of like in Europe and North Africa. There is a last one that is actually around here that makes it an interesting out of distribution station. And you'll see that, it makes it more challenging for the model. We also try to separate between hard cases and easy cases. Hard being they're very different from the previous day, and easy, they're very close to the previous day. So, okay, I won't go in detail. Basically, where it's bold, it's us. So it's good for this station. It's very difficult for this one because this one is the one that is outside of the zone, and it's basically extremely sunny. So these baselines, which are dummy baselines, like you just take the previous day and repeat it, works very well. So basically for sunny places, don't use machine learning. It's kind of useless. Very quickly, this is radar plots to see that our model, of course, is amazing. So it's the red one behind. You see it's good everywhere. This is for unobserved stations, but observed years. But you can see like some of the good models, time series, they do well in easy cases, but not hard cases. This is just visualizations. So here is us, here is the main competition. So you see that, okay, the competition is kind of like smooth, and we kind of get closer to the data, which is good. Unfortunately, I don't have more time. Just to say that we also did a work published at NeurIPS last year that is trying to solve partial differential equation. Basically, you learn the physics directly. And then from there, you can, of course, like if it's like Navier-Stokes, you could predict the weather with it. And this method is just very good at doing super, zero-shot super resolution. So you try to learn on a certain resolution, and it directly predicts at a higher resolution, and it's used graph neural networks for this. But I don't have time again. So thank you guys. You can, of course, come to me or after.